Okay, this is problem, the video two of the death packet, and this is beginning with problem number two. And it says, in general, how does doubling the sample size change the confidence interval size? Well, I think it would really help if you would write this formula down. This is not a formula that you're going to find in the notes, but if you would work with something like this, I think it would help you emit a whole lot. Right? So try this formula out. And I don't think you'll find this online or anything. This is just something I kind of created because it fits what's going on. 1 over the fraction bar, the square root of the new value over the original. So that's going to be 1 over. And I'm just going to take a sample size and I'm going to say, hey, we originally started with a sample, and I'm just going to make it up. I'm just going to say my original sample size was 100. Okay. So let's just say I had an original sample size of 100. You could have chosen 9, 10, 1,000, a million. You choose any number you want. All right. So take that's my original value. I started off with an original, and they said, how does I double the sample size? Well, that means if I double my original, my new is going to be 100 times that, 100 times 2, which is 200. So this would be 200. Well, doing some fancy math, 100 goes into 200 2 times. So now I have 1 divided by the square root of 2. 1 divided by the square root of 2. So let's find out what the square root of 2 is. And I always do caret to the half power. So 1.414. So this is 1 divided by 1.414. So basically, if I double my sample size, I divide my interval by 1.414. And you're like, well, does that always work, Mr. Spencer? Yes, that always works. Try this out. Once again, 1 over new, original. Well, my original, let's take a number. Let's pretend the original was a sample size of 36. I'm going to double it. Well, if I double it, that means my new one is 72. So this is 1 over 36 goes into 72, 2, which is 1 over that 1.414. So this is a really, really good crutch to figure out how things go. And no, you're not going to find that in a textbook, etc. All right. All right. Problem number 3, a confidence interval estimate is determined from the GPAs of a simple random sample of n students. All other things being equal, which of the following will result in a smaller margin of error? All right, so let's look at margin of error. And we have a couple ways of looking at p hat plus or minus z star p hat q hat over n. This is my margin of error. All right, so I need to pay attention to the things that I'm multiplying and the things that I'm dividing. So as z star goes up, I'm multiplying by z star. So as z star goes up, my margin of error goes up. As n goes up, my margin of error, because I'm dividing, will go down. All right. So as z star goes down, then my margin of error also goes down. As n goes down, my margin of error goes up. Well, we wanted a smaller margin of error. So smaller margin of error means I'm either going to want this one or I'm going to want this one. So a smaller confidence level, because Z star increases as my confidence level goes up. All right, so this would be A. Now, standard deviation. Be really careful. All right. And with the standard deviation, if we're talking about proportions, as p hat approaches 0.5, we end up with a larger standard deviation. That's in the numerator. So as p hat gets close to 0.5 from either direction, as p hat gets closer to 0.5, our margin of error increases. On the other hand, if we were working with a t-distribution, then we'd have x bar plus or minus t star s divided by the square root of n. As s increases, our margin of error increases. And I know this because I'm multiplying, all right? But this one is the one that's most difficult. The largest p hat doesn't give me the largest standard deviation. It's the p hat that's closest to 0.5 that gives me the largest standard deviation. Okay. So number 4, a survey was conducted to determine the percentage of high school students who plan to go to college. The results were stated as 82% with a margin of error plus or minus 5%. All right, so what is meant by plus or minus 5%? So what they're saying is it's 0.82 plus or minus 0.05. So that means it can be as low as 0.77 or as high as 0.87. And anything within there we consider plausible values. The true population proportion could be as low as 77% or as high as 87%. So 77.1, really plausible. 86.999, really plausible. 87.01 is outside, not plausible. All right. So it is unlikely that the given sample proportion result would be obtained unless the true percentage was between these values. In other words, they didn't tell us what our confidence level, but we'll just choose 95%. So we are 95% confident the true population proportion lies within here. So it's unlikely that it's something else. All right. And so that's what that best answer is. Just a second. All right, so we're moving on to question number 5. 1 month, the actual unemployment rate in France was 13.4%. If during that month you took a simple random sample of 100 Frenchmen and constructed a confidence interval estimate of the unemployment rate, which of the following would have been true? So let's talk about confidence intervals. First off, the actual unemployment rate is 13.4%. Let's just say, for simplicity, we take a 95% confidence interval. Well, if we take a 95% confidence interval, there's a 5% chance that we don't capture the true population mean. I mean, the true population proportion. This was the true population proportion. 95% confidence interval means there's a 5% chance that that's not going to be in the interval. All right. So if we take an interval, are we assured that the center is going to be p hat? I mean, going to be p. Well, here's what we're assured of. P hat plus or minus z star p hat q hat n. We are assured the center will be p hat, the sample proportion, but it's possible there's a 5% chance that this won't even lie within there. And as we said up here, it could be as low as the lowest part or as high as the highest part. There's no reason we're going to say it's in the center. We're just going to say it's somewhere in there. There's a 5% chance that this isn't even correct at all. So it's definitely not necessarily the center. The interval contained 13.5. Let's just change it to 13.4. No, we're not assured of capturing it. There's a 5% chance that it doesn't have the value. So if there's a 5% chance that it doesn't have 13.4, then there's also a good chance that it doesn't have 13.5. All right, so that's not assured. 99% confidence interval contained 13.4. No, in this case, there's a 1% chance that it didn't. There's still a chance that it doesn't lie within the interval. The z-score of 13.4 was between plus or minus 2.576. No. Z-score 2.54, and by the way, you're like, where in the world did they get that? Basically, if we take a second vars normal CDF and we put negative 2.576, upper 2.576, mean of 0, standard deviation of 1, because it was a z-score, we're like, oh, there's a 99% chance that it was in there. The z-score of 13.4 was between this. No, there's a 99% chance that it's in there, but we're not assured of it. So in this case, none of these are true statements. All right, the margin of error in a confidence interval estimate, this is number 9. The margin of error in a confidence interval estimate using z-scores covers which of the following? Well, first off, what is margin of error? All right, p hat plus or minus z star, p hat q hat over n. Everything to the right, okay? Everything to the right of the plus or minus is our margin of error. So this is my margin of error. Margin of error is a not bias. It is not bias. It is related to sampling error. So sampling error or sampling variability, all right? Sampling error. The reason I'm writing this here, because you might have something and says sampling error. Well, sampling error and sampling variability are the same thing. Please remember, error isn't that anyone made a mistake. It's just that every single sample is an estimate. And because it is an estimate, even if it's carried out correctly, it's still an estimate. And the estimate will be slightly different. It will vary from the true population. So consequently, we say there is error associated with it. All right, so in a survey funded by Burroughs Wellcome, 750 of 1,000 Americans said they didn't believe they could come down with a sexually transmitted disease. Construct a 95% confidence interval estimate of the proportion of adult Americans who don't. So this came from the sample, all right? So in this case, I have a p hat equal to 750 over 1,000. And they're asking us to construct a confidence interval, which is going to follow this formula, p hat plus or minus z star, p hat, q hat, n. Now I'm going to go all the way through this, although the calculator is not going to require me to do it, but I'm going to do it all the way through it so that you'll know how to do that. So we already have the 750 over 1,000. So real quickly, 750 divided by 123, so 0.75. So this is going to be 0.75 plus or minus. We'll come back to z star in just a moment. This is going to be 0.75 times 1 minus 0.75 over my n of 1,000. One other thing while I'm thinking about this, p hat has this formula, which is x over an n. So this means x is 750, n is 1,000. We are going to need that in just a moment. And like I said, if you were showing your work on an FRQ test, you would need to calculate z star. which would be second vars inverse norm, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. We're working with a z, so mean is 0, standard deviation of 1. And I should get about 1.96. All right. So that's if I were showing all my work. Multiple choice test, I'm going to do this much faster. Stat, test, and I'm going to scroll down until I get to 1 proportion z interval. All right. And X is 750, N is 1,000, confidence level of 0.95. And I end up getting 0.723 to 0.776. That rounds, this is probably my best answer. Okay. All right, so this could be a long video. This is covering problems 11 through 20, all of which were requested. So a 1993 Los Angeles Times poll of 1,703 adults revealed that only 17% thought that the media was doing a very good job. With what degree of confidence can the newspapers say that 17% plus or minus 2% of the adults believe the media is doing a very good job? So here we have a margin of error equal to 0.02. All right, we have a margin of error equal to 0.02. And we also have a p-hat of equal to 0.17. So I'm going to go ahead and write down what we know. Here's what we know. We have our equation is p-hat plus or minus z star p-hat q-hat over n. And we also know that n equals to 1,703. And I'm going to get a separate sheet of paper so I have enough room to do this work. So this part of the equation is equal to the margin of error. So with that said, z star p-hat q-hat over n equals the margin of error. I'm going to start filling in what I know and that way we can identify what it is I don't know, what I might need to do. Well, we know that p-hat is 0.17. We know q-hat is going to be 1 minus 0.17, which is just 0.83. We know n is 1,703, and we know it equals a margin of error of 0.02. So the only thing I'm missing is my z star. So let's go ahead and calculate z star and see where we're at. All right. So let's go ahead and calculate z star. So when I calculate z star, I'm going to start off by going 0.17 times 0.83. I'm going to divide that by 1,703. Oops, that's not going to work. Try that again. 0.17 times 0.83. I'm going to divide that by 1,703. And then I'm going to have put in 0.02, and I'm going to just divide it by this ugly number right there. Or try to 0.02, sorry about that, 0.17 times 0.83. What is going on? I'm hitting the decimal point too many times. 0.17 times 0.83 divided by 1,703. I'm going to take the square root of that. Now, 0.02 divided by this number equals 2.197. So z star equals 2.197. And I'm hoping I've done this correctly. So now we were working with a confidence interval. So I just found out my Z star. Please remember, Z is centered on 0. So we know we have a 2.197, which means we also have a negative 2.197. And this is the area that we're looking for in between. So here's what I need to do. Second vars, normal, CDF, lower bound, negative 2.197, upper bound, 2.197. So Z, so means 0, standard deviation of 1. And I get 0.9719. All right, 0.9719. My closest value is this. So basically, I calculated my Z star. And once I calculated my Z star, I had to do a normal CDF. All right, I did a normal CDF right here, with this being my lower, this being my upper, mean of 0, standard deviation of 1 to get that value. So the question came up, and that they recognize that, hey, we know it's the normal curve is symmetric, so that's why I have the positive and negative, but it's a little bit more than that. Remember, our margin of error is a plus or minus value. So I worked it using a positive 0.02. But if I had used a minus 0.02, I would have gotten the exact same thing, but instead of positive 2.197, I would have gotten the negative 2.197. All right. But because, like I said, because it's a plus or minus, I could have used negative 0.02 or positive 0.02, or have done both. In either case, I would have gotten negative 2.197 and positive 2.197. And then we use the norm CDF to find the area or the amount of values or the probability of a value lying between there. And that takes the calculus interval, and that gives me 97.2%. 97.2% of values lie within that interval. All right, this is number 12. A politician wants to know what percentage of voters support her position on the forced busing for integration. What size voter sample, so we're looking for an N, should be obtained to determine with 90% confidence the support level to plus or minus 4%. I don't have a p-hat estimate in this case, all right? So I don't have a p-hat estimate in this case. So consequently, when we don't have a p, well, actually, let me go ahead and write down our formula first. Our formula is p-hat plus or minus Z star p-hat q-hat over n. And this part right here, equals the margin of error. All right. So this part right here equals the margin of error. They're telling me they want my margin of error to be plus or minus 0.04. I can work this problem as a positive 0.04 or as a negative 0.04. Either way is fine. I like working with positive values. I'm less likely to make an error. They also, and we know we're looking for N, so this is going to be my N right there. They also tell me my confidence level is 90%. So I need to find out what my Z star is. So second vars, inverse norm, parenthesis, 1 minus 0.90, close parenthesis, 1 minus 0.90, close parenthesis, divided by 2, mean of 0, standard deviation of 1. And I end up getting about 1.645, and that's what I'm going to call it. I'm going to call it 1.645. All right. So now I know we're looking for this, and I have my margin of error. I have a Z star, but they don't have a p-hat estimate. If I don't have a p-hat estimate, I have to use the value that will give me the worst case scenario. The worst case scenario is always going to be 0.5 because that will give me my largest numerator, which is going to be 0.25. So this is going to be 1.645 times the square root of 0.25 over n equals 0.04. I'm going to divide both sides by 1.645. That's going to go away. And then I'm going to go back and I'm going to use my horrible math and calculate that, square that. So this is going to be 0.25 over n equals 0.04 divided by 1.645 squared. So I'm going to go ahead and calculate that value right there. 0.04 divided by 1.645. And I'm going to square it. So I get a very small value and I need to keep all of this. So, and I've kind of run out of room on this particular page. So on this page, I have, scooting this up, 0.25 over n equals, and I'm going to go ahead and, although I'm going to keep all the decimal places on my calculator, I have basically 0.0059, etc. Well, I'm just going to put this over 1 just because it's easy for me to see that ultimately I'm taking 0.25 and dividing by that number. So 0.25 divided by that small number gives me 422.8. Now this one, it makes sense to round up, but we always round up for sample sizes. This has been 422.001. I still round up. All right, so equals 423. Now, if I look on my sheet and I don't see 423, if it goes from 25, or let's say I had a value at 422 and the next value was 600, I would have to choose 600. Even though it's really 423, you always have to go to the next higher answer. The next higher answer, in this case, we have 422.8. The next higher answer is 423. We have a 423. We're going to choose that as our answer. All right, number 13. In a New York Times poll measuring a candidate's popularity, the newspaper claimed that in 19 of 20 cases, its poll results should be no more than 3 percentage points off in either direction. All right, so first off, let's talk about this. No more than 3 percentage points off in either direction. That means plus or minus 0.03. So this makes this my margin of error value. So that's my margin of error because it's no more than plus or minus 0.03 in 19 of 20 cases. So if I did this in repeated sampling, say 20 times, I want 19 out of 25 to work. Well, 19 out of 25, if I take that and I go 19 divided by 25, that means 95% of the time. So that means it needs to happen 95% of the time. So this is basically a 95% confidence interval. 5% of the time, it's not going to capture, but 95% of the time, it's going to be no more than this. So 95% of the time, it's going to capture it within plus or minus 0.03. So this gets rid of these. We know it has to be one of these 95% problems. So when we go to our confidence interval, once again, our formula, p hat plus or minus z star, p hat, q hat over n. This part being our margin of error. And they told us its point can't be more than 0.03. They're looking for a sample size, which is going to be n. We don't know what that is. They did give us very cleverly, they told us that it needs to be a 95% confidence level. So I need to calculate a z star. So second vars, inverse norm, parenthesis 1 minus 0.95, close parenthesis, divided by 2, mean of 0, standard deviation of 1. and I end up getting 1.96. So this is going to be 1.96 as my Z star value. And then I look to see, do I have a p hat? Well, I don't have a p hat, so whenever I don't have a p hat, I have to use the worst case. The worst case is the one that gives me the largest numerator, and the worst case p hat is always going to be 0.5. This will be an always. If they don't give you p hat, you have to do an estimate, use 0.5. So I'm going to take both sides and divide by 1.96. This goes away. So this is going to give me 0.25, because this times this is 0.25, over n equals 0.03 over 1.96. I'm going to square both sides. When I do that, I end up getting 0.25 over n equals 0.03 over 1.96 squared. So 0.03 divided by 1.96 raised to the second power. And then I'm going to take 0.25 and divide it by that really small number. And I get up 1067.1. All right. I always have to round to the next highest value. The next higher value than 1067.1 is 1068. This is my answer. Now, had they given me, let's just say D had equaled 1067 and E was 2500. I always have to round to the next highest. This is too small, so I'd have to go to the next highest value. Regardless of how far away it is, always go to the next highest. All right, number 14. Which of the following is an incorrect statement? And by the way, this actually kind of ties back to question number 1. You're like, question number 1 was a proportion. I know, but it's about unbiased estimators, and this is actually related to that. So the sampling distribution of X bar has a mean equal to the population mean. By the way, we're looking for incorrect statements, so we're looking for false. The sampling distribution has a X bar mean equal to the population mean. That is true. Our assumption is X bar is an unbiased estimator. We believe X bar equals to M. So that's true. We also believe that P hat equals to P. The sampling distribution of P hat equals the true population proportion. This is true. We're looking for false, so that can't be our answer. The sampling distribution of X bar has a standard deviation of this, even if the population is not normally distributed. Not normally distributed. This is true. That is the standard deviation of X bar. All right. Now, it may not become normal. It won't become normal till n is 30 or larger, but that is the standard deviation of X bar. That's the formula for the standard deviation. The sampling distribution of X bar is normal if the population has a normal distribution. That is true. If the sampling distribution is normal, regardless of the sample size, if the underlying population is normal. Because remember, the sampling distribution, the distribution of X follows the underlying distribution. And if the underlying distribution is normal, then obviously it's normal. When n is large, the sampling distribution of X bar is approximately normal. That's true. We define n as large as n greater than or equal to 30. So if n is greater than 30, X bar is approximately normal. Lastly, the larger the value of the sample size, the closer to the standard deviation of the sampling distribution of X bar is to the standard deviation of the population. And you're like, Mr. Spencer, as n gets larger, it gets closer to the normal. You're right. As n gets larger, it does get closer to the normal. But this is the standard deviation of the population. The standard deviation of X bar is this. So as n gets larger, this gets smaller, which means it's actually getting farther and farther away from that, because we're taking the standard deviation of the population and dividing it by the square root of n. So the standard deviation of x bar has this formula, all right? And as n gets larger, this gets smaller, which means it gets smaller relative to the population standard deviation. So this is our first incorrect statement. I'm having trouble with the. All right, number 15. In a large school of 2,500 students, the students in an AP class are planning a random survey of 100 students to estimate the proportion who would rather drop lacrosse rather than band during this time of severe budget cuts. Their teachers suggest instead to use a survey of 200 students. Well, let's go ahead, and since we're estimating the proportion, that means, if we're estimating, that means we must be doing a confidence interval of some sort. So p hat plus or minus z star, p hat q hat over n. If I increase n, as n goes up, this gets smaller because I'm dividing it. So as n goes up, my margin of error goes down. Margin of error goes down. All right, keep that in mind. Sample size has nothing to do with bias. Bias is bad design. So anything with bias is gone. All right. Now, as n goes down, my margin of error goes down. As n, and this part right here is actually known as my standard error. As an error generally refers to variability. So as n goes up, my variability goes down. All right. My margin of error goes down, so my variability is going down. Number 15, suppose that 35% of all business executives are willing to switch companies if offered a higher salary. So this is the claim. So HO, P equals 0.35. If a headhunter contacts a simple random sample of 100, what's the probability that over 40? All right, so we want to know that it's greater than, so our alternative is P is greater than 0.35. And they're telling us P hat equals 0.40. So if I'm setting up my equation, I want the probability that Z is greater than P hat minus P naught over P naught Q naught N, which is the probability that Z is greater than 0.40 minus 0.35 over the square root of 0.35 times, that looks horrible. Apologize for all of you watching. And we had a sample size of 100. All right. But I'm going to run into a problem when I get to my calculator, because my calculator is not going to ask me for P hat. They're going to ask me for X and N. Well, P hat equals X over N, which in this case, P hat equals 0.4 equals X over 100. All right. Please remember X and N must be whole numbers. So we're going to go stat test number 5, one proportion, Z test. The claim, 0.35. The X, that's going to be 0.4, 0.4 times 100. And I need to check, is that a whole number? If that had been 40.1, I would need to round to 40. If it had been 39.7, I'd need to round to 40. Always round to the nearest whole number. N needs to be 100. And by the way, please notice I took P hat. I went 0.4 times 100. So P hat. All right. My alternative hypothesis was a greater than because they wanted to know that it was greater than this. And we calculate. And I end up getting a P hat of about 0.147. The closest one that I have right here is 0.1465. All right, so this is my closest probability. By the way, I knew that this was a hypothesis test and not a confidence interval because they gave me an initial claim and they didn't ask me to use an interval. Further, they gave a direction. They said over 40%. So they gave me a direction. If they give me a direction, I have to use a hypothesis test. Question came up. Do we use P or P hat in our statements up here? This is, I don't know why that says P hat. That is completely a mistake. Thank you for catching this. Your hypothesis statements are always based on P or P naught. So P is 0.35, P has to be greater than 0.35. I'm so glad that they caught me and said, do not use sample statistics here. They will always either be mu equals if we're doing a test for means, or they're going to be P equals if we're doing a test for proportions. Do not use P hat values here. Do not use sample statistics here. These must be population statistics, either the population mean or in this case, the population proportion. Thank you for catching me on that so I could get that corrected. All right, so the question is, how did I know to use 40% as my P hat? How did I know to make this that? So remember, P is, well, the null hypothesis is based on the initial claim. Well, the initial claim is so 35% are willing to switch. That's they're telling me is the true population. They're telling me this is the true population. What's the probability that that in a simple random sample? So what's the probability I get a sample? And so this means, oh, what's the probability I get a sample value of 40%? So this tells me that what's the probability that I get a sample value, and P hat is the definite, it means a sample proportion. So what's the probability I get a sample proportion of 40%? So because this is a sample proportion is why that is my P hat. All right, so here's what someone asked. Phenomenal question. And honestly, I'm really glad someone finally got around to asking, because I think this is one of the most difficult things at this point of the year. How do we know which of the different types of tests? A Z, a T, a one proportion, a two sample, etc. This is like the ultimate question at this point of the year, as far as I'm concerned. So real quickly, if we're dealing with proportions, first off, it's either going to be a one proportion Z or a one proportion T. So if you're working with proportions, it's going to be a one proportion Z or a one proportion T, or a confidence interval of proportions, but regardless, proportions work with Z's. Proportions will always refer to a Z. They will never refer to a T. So that will help a little bit with that. That doesn't get us everything we need to know on that question. This is a big question. So proportions are going to be working with a Z always. So when are we using a T? Specifically, we're working with a T when we're working, well, first off, we're working with a T if we're working with means / X bars. So if we're working with means or X bars, we're working with a T, assuming we're using the sample variation or sample standard deviation. So a T, regardless whether it's a one sample or a two sample, means that we're going to be using the standard deviation of the sample. So standard deviation of the sample, assuming it's not a proportion, proportion is always a z, but if we're using the standard deviation of a sample and we're working with a mean, it's going to be a t distribution. So standard deviation of the sample, in other words, you use S. If you're using S, it's going to be a t distribution. All right. And the question is it going to be one sample t or two sample t? A one sample t means we have a claim and we're comparing a sample to that t. With a two sample, we have two sets of data. We have two independent samples. All right. We don't have a claim and another group. We have two separate groups working with X bar and having a standard deviation from the samples is an S. Okay, not sure if that helps or not, or gets it all the way through. All right, so you will use a sample standard deviation because they'll say the standard deviation came from the sample, in which case they'll tell you the standard deviation came from the sample, in which case you have a T. Or if they give you a list of data and they don't give you a population standard deviation, then you have to use that list of data to calculate it. But please be careful. If you're working with proportions, then it's a Z. All proportions are a Z. All right, and one other thing on the T. You use the T when you're working with means and you don't know the standard deviation of the population. If you're using the standard deviation of the sample and you're working with means, you have to use a T. That is a prerequisite for the T, is that you're using the standard deviation for the sample and you're working with means. All right, so the question was asked, what's the difference between two sample and paired? In general, in paired distribution, you have something that is tested twice. It might be a before situation and an after situation, but I got tested twice. Or I'm paired with a specific individual. I could be compared to my wife. You can compare what are the difference in IQs for couples. Well, you can look at my IQ versus my wife's IQ. Okay. Or in which case we have a natural pairing. So something that we're actually natural paired, where with a two sample, we have two independent groups. We could have the group of married men and a group of married women. So we took the average IQ of all the married men, and compared it to the average IQ of all the married women. But the groups are independent groups. There's not a pairing. There's not a natural relationship. Obviously, there's a natural relationship if you're comparing me directly to my wife, or comparing one of my children to me, or if I was tested twice. They're really not, to be honest, that's not really an independent sample. That is a single sample because there's a relationship. All right. Number 17, given that 58% of all gold dealers believe that next year will be a good one to speculate in South African gold coins in a simple random sample of 150 dealers, what's the probability that between 55 and 60% believe that it will be a good year to speculate? All right. I'm going to pause this for a second because I haven't worked this problem in a while. Okay, so with this particular problem, I'm not thinking of a very specific shortcut. There's a couple ways we can approach this thing, but I'm going to go ahead and do this in a long form fashion because I think this will make more sense if I do go through the long form fashion of this problem. So in this particular space, that's given that 58%. So that means we have a claim of 50%. So P equals 0.58. All right. In a random sample, What's the probability that between 55 and 60%? So I'm going to go ahead and draw this graph of what we're actually talking about. Reality is 0.58. That's reality. And that's P. Well, what's the probability that I get a P hat as low as 0.55 or a P hat as high as 0.60? So I'm really looking for this. Well, this is starting to look like a norm CDF because we know that if we take 150, if we take 150 times 0.55, we're going to get greater than 10. So basically, we're going to be large enough to use the normal approximation, because in both cases are going to be greater than 10. So what's the problem with doing the norm CDF is I'm going to need a mean and I'm going to need a standard deviation. Well, my mean is actually in this case going to be 0.58. That's my true population proportion. Well, what's the standard deviation for that? The standard deviation is going to be 0.58 times 0.42, 0.58 times 0.42 over my sample size of 150. 0.58 times 0.42 times my sample size of 150. So let's do it this way, and then I'm going to show you one other way to think about this. So second vars, normal, CDF. My lower bound as low as 55%, 0.55. My upper bound as high as 60%. My mean, well, what was my expected center? My expected center is 0.58. Now this one is going to get a little bit, 0.58. This is why I pause, because it's a little bit ugly to do this. So I'm going to go parenthesis 0.58 times 0.42, divide that by 150. I'm going to close my parenthesis, and I need to take the square root, so I'm just going to raise that to my half power. And I end up getting this value of 0.4619. Now, some of you probably don't like that a bit, and that's fine. I'm going to show you a different format. Let's go ahead and do this as a stat test. Well, if we're doing this as a stat test, I need my p hats. And my p hat is either 0.60 or my p hat is either 0.55. If I do a p hat of 0.60, my x is going to be x over n. All right, so let's go ahead and do that first one. So stat test, one proportion z test. My claim was 0.58. My x bar would be, if I'm doing the 60% one, 0.6 times 150. That's my x. It's a whole number, so we're good to go. My n is 150. And just do a less n. I'll come back and talk about that in a moment. And I get a p-value of 0.69015. So 0.69015. That's for the 60%. I'm going to come back and I'm going to subtract out the 55%. So we're going to do the same thing again, but for 55%. So stat test, one proportion z test. My p naught, that's my original claim of 0.58. X is going to be 150, the sample size, times the 0.55. My sample size is still 150. Oops. That's always disturbing when that happens. 0.55 times 150. Oh, that's why it happened. Stats test, one proportion, z-test. So I got an 82.5. That's not going to work. 82.5, normally I'd round up, so I'm going to round up to 83. This means I'm going to have a little bit of error in my problem, but that's okay. And I end up getting a p-value of 0.254. Let's subtract these two, see how close we are. 0.69015 minus 0.254. 0.436, so my closest value is 0.4619. All right, difficult problem, and I'm not sure the best way. Hopefully the questions that I'll be asked will help it clarify. In a random sample of 1,250 adults, 450 said that they would cut their driving by 10% if this significantly helped the environment. Find a 95% confidence interval to estimate the proportion of adult drivers who are willing to cut their driving by 10% to help the environment. All right, so first off, they tell us they're looking for an interval. So I know I have to work with an interval, and we're working with proportions. So my formula is going to be p hat plus or minus z star p hat q hat n. Well, p hat equals x over n, where n is the sample size, x is the number of successes. So in this case, 450 over 1,250. 450 divided by 1,250. So there's our 0.36. All right, so this is going to be 0.36 plus or minus. We'll come back to z star in just a moment. 0.36, 1 minus 0.36 over 1,250. And then we need to calculate our z star, second vars, inverse norm, 95%. So our area is parenthesis 1 minus 0.95, close parenthesis, divided by 2. And we end up getting 1.96. Here we go. A 2007 survey of 980 Americans concluded that 38% of the driving population will be willing to pay higher gas prices to protect the environment. Which of the following best describes what is meant by the poll having a margin of error of 3%? So first off, they're telling us p hat plus or minus our margin of error. So they're telling us 38%, so 0.38 plus or minus 0.03. So that's going to be a low of 0.35 to a high of 0.41. I subtracted 3%, I added 3%. So I don't know what the confidence level is. Let's say it was 95%. So we're 95% confident that this is the true proportion they're willing to pay that. The 3%, this not so good. It just doesn't really apply. It basically tells you how far it is. So it's likely that between 35% and 41%. Matter of fact, 95% confident that it's between 35 and 41%, or whatever the confidence level. So they're saying likely. We are reasonably confident it's between 35 and 41%. We'll be willing to pay a higher price on that. Number 22, a survey of 1,000 Americans reveals that 525 believe that whales are an endangered animal. and should have protection from the fishing industry. A survey of 750 Japanese, 325 believe that whales are endangered and should be protected. To test at the 5% significance level whether or not the data are significant. The proportion of Japanese is less than the proportion of males. A student sets up the test where P is the proportion of Japanese. All right. Here we have two independent groups. We have a group of Americans and a group of Japanese. We have two independent groups. We'd be better off saying, hey, is the proportion of Americans less than the proportion of Japanese? Because we have two independent groups, a two population difference in proportions would be more appropriate. This is not a single sample, all right? There's not an initial claim. Now, if there was an initial claim that 52% of the world believed this, how does Japan compare to the 52% of the world? We could do that or something like this, but we are actually comparing the Japanese population to the American population. So consequently, we have two proportion groups, and we actually a two sample in this case makes much more sense. Further, we have a survey of Japanese and we have a survey of Americans. So we have two independent samples. A guidance counselor wishes to determine the mean number of changes in academic major by college students to within plus or minus 0.01 at 90% confidence level. What sample size should be chosen if it's known that the standard deviation is 0.45? All right, this is an ugly problem and is a bit concerning. They're telling us our standard deviation is 0.45. Because they're telling us our standard deviation is 0.45, we're sort of working with an X bar plus or minus Z star sigma divided by the square root of n. You're like, how did he know all of that? All right. They're telling me they know the population standard deviation, so it can't be a T. And by the way, this is unlikely to see a problem like this show up. So it can't be a T because they tell me they know the population standard deviation. So this is 0.45 over the square root of n. We know the 90%, so 90% needs to be second vars inverse norm, parenthesis 1 minus 0.90, close parenthesis, divided by 2, mean is 0, standard deviation of 1. So this ends up being 1.645. And my margin of error, they said they wanted it to be plus or minus 0.1. So I'm going to go ahead and multiply these two values. So 1.645 times 0.45. Just a moment. I'm sorry about that. So 1.645 times 0.45. So I end up with 0.74025 over the square root of n equals 0.10. And if I do some mathematical manipulation, I end up getting, if I swap these around, I end up getting 0.74025 over 0.10 equals the square root of n. So I'm going to go ahead and divide that by 0.10. And then I need to square root this whole, raise this to the second power to take that off. So just square that. And I got 54.79. And the next highest value is 55. Number 24, an office manager believes that the percentage of employees arriving is even greater than the previously claimed 7%. She conducts a hypothesis test on a random sample of 200 arrivals and finds 23 punching in late. Is this strong evidence against the 0.07 claim? So basically, in this case, our null hypothesis is P equals 0.07, and she says she believes it's greater. So our alternative hypothesis is P is greater than 0.07. P hat is going to equal X over N, where X is 23 out of 200. And I'm not going to show my work on this. I'm just going to go straight to the calculator at this point. So stat test 1 proportion z-test. P naught, that's the claim, 0.07. X was 23. N was 200. Greater than, took the interval, and we end up getting a p-value of 0.006. All right? So is this strong evidence? Well, p-value of 0.0062 is very, very strong, because if we have our p-value and we have an alpha, if our p-value is 0.0062, if I take an alpha of 0.050, this is less than, so we're going to reject the claim of 7%. So we're going to reject the claim, so this is strong evidence. Anytime you reject it, you're going to, anytime you reject, you're considering it's strong evidence, and it really wouldn't matter which alpha level you chose. That's a pretty small p-value. That's a low p-value. Okay, so the question was, can you go straight to the calculator? The answer is it depends. If it's a multiple choice test, which you're taking next week, go straight to the calculator. You only need to write down what you need to write down. And what that means is, if you need it to help yourself out, write it down. Otherwise, you don't. You do it as fast as you can. Remember, there's a time limit. So on the multiple choice section, you write down what you need to write down. If it had been a FRQ section, which you don't have next week, then you would have to write all down. But with a multiple choice test, no, you're just going to go as fast as you can. But on an FRQ test, you're going to have to write down the formulas, the equations, the plugins, and the conditions, etc. All right, number 25. I'm not going to go into great detail unless there are follow-up questions. It says, which of the following is a true statement? When we're running a hypothesis test, we never try to prove the null. So we're not gathering evidence to prove the null. In fact, we never do. What we do try to show is that the null is false. So we're gathering evidence against the null, right? It's the court of law. I'm prosecuting, I'm gathering evidence against the defendant. So I'm making a case against the null. So my answer is A, I'm gathering evidence against the null. Is there enough evidence? That's why our statement says we have sufficient evidence to reject the null, or we do not have sufficient evidence against the null. Two confidence interval estimates from the same sample are 72.2 and 77.8 and 71.3 and 78.7. One estimate is a 95% level and the other is at the 99. Which is which? Well, when I look at these, I'm just going to take these intervals and I'm going to just take this one 77.8 minus 72.2. So this has an interval width of 5.6, and then 78.7 minus 71.3. This has an interval of 7.4. So this interval is wider than this one, right? This is narrower, this is wider. And they're from the same sample. The reason that's important, that means they have the same standard deviation. One estimate is at 95, one is at the 99. As your confidence level goes up, the margin of error goes up. This one's wider. That means it has a larger margin of error. So as it gets wider, larger margin of error. So 72.2. So the first one has a 95%. All right. This one's at the 99%. So this is correct. A is at the 95%. I think this number 27, I believe, is a repeat question. But that said, I'm going to reintroduce this formula because I think it really does help. So when you're trying to figure out how sample size is affected, you probably want to go ahead and memorize this formula unless or a lot of my students like this. 1 over the square root of the new over the original. So 1 over the square root of, now they did not give me any sample size. So I'm going to just create a sample size. I'm going to say I originally started with a sample size of 10. All right. Now they tell me I'm doubling it. So if I started off with a sample size 10, and I could have chosen any number, it wouldn't matter. The new sample needs to be twice as big as this because they said double it. So twice as big as 10 is 20. Well, 10 goes into 20 twice. So this is 1 over the square root of 2. Well, I know that the square root of 2 is 1.414. So it's 1 over 1.414. So I'm ending up dividing the interval by 1.414. And I know I'm dividing because it's in the denominator. Number 28, a confidence interval estimate is determined from the summer earnings of a simple random sample of n students, all other things being equal. Which of the following will result in a smaller margin of error? So we want a small margin of error. So a greater confidence level. As confidence level goes up, margin of error goes up. Can't be that because we wanted a smaller one. A larger sample standard deviation. All right. So as my standard deviation goes up, as S goes up, my margin of error goes up. A larger sample size. As N goes up, my margin of error goes down. All right. So this one is C. As N goes up, my margin of error goes down. These two don't apply. Those two don't apply. Should there be more restriction on handguns in a 1995 pre-Columbian survey, pre-Columbine survey? And I remember where I was on that day when that happened and watched it happen live. Rough day. 255 out of 1,020 adults answered in the affirmative. In the 2000 post-column survey, 352 out of 1,100. So we have two independent samples, one pre-Columbine, one post-Columbine. So we're subtracting them, all right? And so we're going to basically have a p hat 1 and a p hat 2. Our formula is basically this: p hat 1 minus p hat 2 plus or minus z star p hat 1 q hat 1 n1 plus p hat 2 q hat 2 n2. That's our formula. So I need to be that right there. So this is gone without doing any work. That's gone. And then I need to sit there and go, all right, what else can I do fairly quickly? Let's go ahead and look at our Z stars. They said they wanted to do a 90%. Second vars, inverse norm. Turns out I already have it there, but parenthesis 1 minus 0.90, close parenthesis, divided by 2, mean a 0, standard deviation of 1, calculate. And I end up getting 1.645. The only one that has that is this one. The rest of them don't. I'm done. Now I could have gone back and checked all the p hats because 255 out of 1020 needs to give me 25%, and 352 divided by 1100 should give me about 32%. So 29 should be A. The acceptance rate at a particular college is 58%. If one takes a simple random sample of applicants to this college and constructs a confidence interval of the acceptance rates, which of the following is true? The center of the interval is 58%. That would be nice. But our formula is this: P hat plus or minus Z star, P hat, Q hat, N. P hat is the center of the interval. 58% may not even be in the interval, because if we do a 95% interval, there's a 5% chance that 58% won't be in it. P hat will be the center, it will always be the center. It may or may not be P. So that's not going to happen. The interval would contain a 58%. We just said that there's a 5% chance that wouldn't. A 99% confidence interval would contain 58%. No, there's a 98%, 99. If we do a 99% confidence interval, we're 99% confident that the proportion would lie within there, but there's a 1% chance that it would not. Obviously, we got rid of more than one, so all of the above are not true. E, ain't none of the statements true. We all lied all the way around. And he said in his Texas accent.